All right. We discussed, or are there any questions? Still got 1 minute. Okay. So we discussed last time the definition of morphisms of schemes. Which includes the sort of obvious things you would definitely want to have, which is a continuous map on the underlying topological spaces, a pullback map on functions, so remember this goes from a map of sheaves of rings on Y from O of Y to the push forward by pi of O of X. This maybe looks a little more natural as a pullback map if you say, okay, what does this tell me on each open set? It tells me that if I have an open subset of Y, then I get a map from functions on U on Y to functions on X of pi inverse of U. And that is indeed what a pullback map would do. It would turn a function on Y into a function on X. But then we need an extra condition on this. So this would be a morphism of ringed spaces, but we actually want to remember this sort of extra structure that comes with being a scheme, which is that the stalk of the structure sheaf is always a local ring. And that local ring structure really is part of the geometry, because being in the maximal ideal of that local ring is what it means for a function to vanish at a point. Right? Remember that the stalk is kind of remembering not just the value at the point, but sort of a larger radius around it. So if I look at the stalk here, you should think of this as kind of like the Taylor series of functions. Taylor series is obviously like a little, so that's like a little dubious as a metaphor, but that's kind of the thing you should think about, that it really is containing kind of local information about what's happening around that point. Whereas if I look at this guy, mod its maximal ideal, that's the actual values of the functions. This is what's called the residue field. People will generally use that word for local rings, that the local ring mod its maximal ideal is the residue field of the local ring, but you'll also hear this said as the residue field of the point P. And the usual notation for this is little k of P. And certainly one of the sort of important ideas about schemes is that points have different functions attached to them, which kind of, fields attached to them, which kind of tells you how big the point is. So for example, right, if I look at spec of Rx, right, we've discussed that this guy has this kind of odd structure of having a copy of the real line and then kind of half of the complex plane, or it's really better to think of this as the complex plane folded up using modding out by the automorphism of conjugation. But if I have a point here, the residue field is going to be C. If I have a point here, the residue field is going to be R. And there's also one more point. There's the one corresponding to the zero ideal. So there's also a generic point whose residue field is rational functions. Oh, I should use the same variable, rational functions with values in the real numbers in terms of X, right? And so the fact that this point is bigger than one of the closed points is expressed by the fact that this field is bigger. Bigger in what sense? Well, it has transcendence degree 1 over this field. Right? So transcendence degree is one sort of useful way of measuring size. For example, this is something we prove in the commutative algebra class. And I'm sure we'll discuss later when we discuss dimension. But if I look at an algebraic variety over C, one of the ways of defining its dimension is the transcendence degree of its function field over C. Right? So the fact that this is a ring with Kroll dimension 1 is expressed in the fact that this generic point has a field of transcendence degree 1 over the base field. Okay, cool. So I didn't actually finish my definition here because I got distracted talking about local rings and residue fields. I want an extra condition here, which is such that I have an induced map from the local ring on Y. So sorry, I've been trying to say stalks to avoid confusion with the notion of local ring in commutative algebra, but these are called local rings in algebraic geometry as well. So the stalk at the image of a point P in X pull back to the stalk at that point, right? And this is if I have a germ around the image of P, the pre-image of U is a neighborhood of P. So this gets sent to the germ phi sharp of phi inverse of U. And this pi sharp, this is the name of this map from functions on U to functions on the pre-image in X. So, I mean, that's also a useful notion of size, right? So the way you would think about that is, I haven't finished my sentence. Let me finish my sentence here and then we can talk about this. Such that, so I want this to be a morphism of local rings, which means that if I take the pre-image of the maximal ideal in O of xp, that's equal to the maximal ideal in y of I of p. And the thing I would worry about is it could be smaller, right? The pre-image of this is always a prime ideal, so it's always contained in the maximal ideal, but it might be smaller than the maximal ideal. Okay, so let's talk about examples of this. So one example that someone was just asking about is if I have a field extension, L over K, well, I have a map that goes the other way from spec of K, which is a point, to spec of L, which is a point. And the way you should think about this is a cover whose degree is a degree of the field extension. This is like a finite covering. And that might sound slightly insane, but of course, I have situations where I have actual like algebraic varieties over C, and I would have a finite to one covering. And then what's the relationship between the function fields of these guys? The function field of this guy will be a finite extension of the function field of this guy. So this happens if, let's say, these guys are integral. So Let's call this X, let's call this Y. The function field, let me just write the notation, K of X contains K of Y. So this guy has a generic point. This guy has a generic point. The map sends the generic point to the generic point. And so I'm looking at the pullback map on stalks at the generic point. Gives me an inclusion here. And this is going to be a degree D. So this is a D to 1 map. This is going to be a degree D field extension. So somehow what I'm doing here is I'm saying, well, I should pretend every field extension really comes this way. You know, there are field extensions which definitely aren't the function field of a variety over C or something. But if I have some other field extension in some other context, even if I can't sort of really interpret it this way, I'm still going to think secretly that's what's going on, that it's a D to 1 covering. And you know, you can sort of coherently define all these notions of what it means to be a D to 1 covering, and this will sort of satisfy them. Being a field means it's kind of somehow a connected covering. Because of course you can, you know, get D to 1 maps by, you know, having like 3 copies of the same thing mapping here, right? But that's not going to give you a field extension. So somehow the fact that this is a field extension is exactly kind of interpreting the fact that this is integral and not like a big union of things. All right, cool. All right, are there any questions about that stuff? Okay, so this seems like a slightly weird definition. Why did I include this? The reason I included this, as you know, sort of Vakil explains, is that I need this condition to force maps between affine varieties to actually come from ring homomorphisms, right? So theorem is phi from spec A to spec B is a morphism of schemes then there are sort of 2 things I can do to a prime ideal. So one thing I can do is I can take a prime ideal in A, and I can apply this map P to it. But I can do something else. I can remember that A is the global functions on spec of A. And B is the global functions on spec of B. Which means that pi sharp is a ring map from B to A. All right. So the other thing I could do is I could take a prime ideal here. I could look at its pre-image, and I could think of that as a point in spec of B. All right. And it's something worth checking that these are the same. Right. So we saw that if I only looked at morphisms of ring spaces, there are morphisms of ring spaces between spec A and spec B that don't satisfy this condition. We saw this with spec A equals Q and B equals Z. There are maps of ring spaces from spec Q to spec Z. Let's send the one point in spec Q to a closed point. And I don't want that to be a morphism of schemes. And indeed, what goes wrong is my map here ends up being a ring homomorphism, which is not a morphism of local rings, right? I get the map from ZP into Q, right? And exactly the problem here is there are elements of the maximal ideal here that map to units here, right? So another way to say this condition is that if I have something which is not a unit, which is in the maximal ideal, and here, it maps to something that's not a unit here. All right, so this is one of these theorems that it's like a little hard to prove because it's really kind of like just writing down the definitions and being like, oh, yeah, okay, cool. But we should at least write down the definitions. So what am I gonna do? I'm gonna look at let Q be phi of P. All right, and my map pi natural induces a map between the local rings. Do oh, I'm drawing this the wrong way. Sorry. Needed to look at the picture in my notes. So B, BQ. How much chalk did I just get on the shirt? Not too bad. All right. So the punchline here is if I have two prime ideals such that I have an induced map between the local rings, and that is a morphism of local rings, that means that Q is the inverse image of P. Okay? And so one just has to write that down. What do we have to check? Well, the thing we're worried might go wrong is that we might start with an element of Q. And we're worried that that might, right, sorry, what I want to see that Q is the inverse image of P. All right, so the fact that I have this morphism of local rings at all tells me that if I have something in Q, that maps here, that maps to an element of the maximal ideal here. And it being a morphism of local rings tells me that that maps to an element of the maximal ideal here. So this is just sort of annoying to write out, because you just say, okay, if B is in Q, well, then it's in the maximal ideal. If I think of it as an element BQ, so that means that when I look at its image under pi natural, that's in P of AQ by assumption. So this is the thing that wouldn't necessarily be true if I hadn't added this assumption. So using this assumption to say that actually it has to land in this ideal. Well, this is also an element of A. So it's actually in this guy intersect A, which is the same thing as P. All right, and similarly, if B is not in Q, then that means that B is a unit in BQ. So this image is a unit in AP, which means that this guy is not in P. All right, so this is an automatic thing for any ring homomorphism between local rings, that it has, because a ring homomorphism sends invertible guys to invertible guys, you can only get a map between the local rings when the pre-image of P is contained in Q. The tricky thing is the inclusion the other way. Okay, so that completes the proof. I just saw that Q is the pre-image of P, exactly. All right. So one thing that's worth checking here, so there's sort of a little more detail to check, which is not just that it's the same map on points as this, but I actually described a map of schemes that you get from this, where you have to also pay attention to what happens on distinguished open sets. But it's basically you look at the same diagram, but localizing at particular elements instead of localizing in prime ideas. And you say, well, that's since everything has to be compatible with restriction, right? One thing I was using here is everything has to be compatible with restriction. The maps between open sets have to be the only ones you could imagine they are. All right. And that's dealt with in more detail in vacuous, so you can read that. Another important idea is that, as I said, this is sort of the same as declaring that my homomorphism has to locally look like these maps coming from homomorphisms. So theorem, a morphism of ring spaces is a morphism of schemes. So it satisfies this local ring condition. If and only if there exists UI and VI. So the UI in X, the VI in Y. Affine open covers such that psi of UI is in VI, and the homomorphism from UI to VI is induced by a ring homomorphism. Okay, so what this is telling us, right? It's now sort of obvious once you know this fact, right? That if I have a morphism of schemes and then I pick an affine open cover like this, well, the way I defined morphism of schemes, it's obviously compatible with restricting to an open cover because everything is sort of a local condition. And so this is a morphism scheme of schemes from UI to VI, and that theorem tells me that it has to come from a ring homomorphism. The restriction of pop, right? I exactly required that it makes sense. So, I mean, oh yeah, sorry. Morphism on stalks. Well, I mean, it's both, right? It's the same. So, I mean, right? I mean, I could write pi sharp sub p here, like that it's, or should actually write sub p sub p, right? But the point is, this is the same as b thought of as an element of a. So, I mean, the point of a morphism of local rings is that it sends units to units and sends non-units to non-units. Whereas if I have general ring homomorphism between local rings, it might send things that aren't units to units. Yeah. Yes, sorry. Yes, I should have said between schemes. And why? Now, I mean, of course, if you read this, this condition implies that X and Y are schemes. So, I mean, somehow, yeah, if I tried to apply this to ring spaces which weren't schemes, I would just find, oh yes, they're not schemes, so it's not a morphism of schemes. All right, any other questions? Okay, so I was kind of halfway saying the proof out loud. I won't try to write any details, but the other direction, that if I have a cover like this, then I get a morphism of schemes, is again just that the morphism of schemes is a local property, right? So on an open cover, I can test whether I have a continuous map. I can test whether I have a pullback map of sheaves. Um, and I can test whether the map on stalks is a morphism of local rings or not. So this is really a special case of a much more general principle, which is morphisms of schemes glue. So if UI is an open cover, X, I don't need to assume that the UIs are affine. I could, but they don't have to be. And let me call it pi I. Pi I UI to Y is a morphism. And if I take pi I and I restrict to the intersection of UI and UJ, and that's equal to UI and UJ. Then these morphisms on the open cover glue into a morphism on the whole guy. Then there exists pi from X to Y, such that pi restricted to UI is equal to pi. All right, and the fancy categorical way of saying this is that I'm telling you that X is a co-limit where I take these UIs and then I glue together over the inclusions of UI intersect UJ. So I could write this as a push-out diagram in the category of schemes. But this is also just right? Everything there, I have to tell you where each individual point goes. I have to tell you on an open cover, right? A morphism of sheaves only needs to be described on an open cover. And I need to check a condition on the maps of the stocks. Well, all of those are things I can do locally on an open cover. And that's useful because, of course, schemes which aren't affine are usually described in some way so that we have an affine cover. All right. Yes. Comes from a ring homomorphism. So for example, one useful example of what morphisms of schemes look like is morphisms from an arbitrary scheme to spec A are in natural bijection with ring homomorphisms from A to the global functions on X. Right? We already talked about this for affine schemes, that all morphisms between affine schemes come from ring homomorphisms between the rings. But a more general thing is any map to an affine scheme comes from saying, I have the functions on here, what do they pull back to? So if this map is pi, this is the map pi sharp, where I interpret A as the global sections on spec A. All right, and the proof is choose an affine open cover of X by UIs. So all of my UIs are affine schemes. All right, so a morphism from X to spec of A, well, I can use this gluing principle. So that's the same thing as morphisms from UI to spec A that agree on the overlap. All right, well, that's the same thing as ring homomorphisms from A into the global to the functions on U of I that agree on the overlap. And I probably have to do a tiny bit of work here. I'm being a little cavalier about like, oh, is it totally obvious? So certainly a morphism from UI to spec A gives me a ring map. The question is, what does agree on the overlap mean? I think I'm probably okay. Um, I just have to use that I have a cover of the overlap by affine schemes. I was a little worried about that if I'm not quasi-separated, but I still have a cover of the overlap. It's just not finite. That's okay. Okay. So I have these ring maps. Well, now I use the gluing property of sheaves, right? If I have an element of A I get a section on each of the UIs, and they all agree on the overlaps. Well, that's the same thing as telling me a global section. So because of this sheaf property, I get that this is the same as a ring map from A to O of X, global functions. Yeah, yeah. Well, I mean, again, what's the data of the map? It's where every point goes. That's obviously unique because every point lies in one of the UIs. It's what's the map on sheaves? That's obviously unique because a map on sheaves is determined by what it does on stalks, and every stalk is in one of these open sets. And that's all the data, right? The third thing is a condition. It's true or it's not true, but it's not extra data. Sorry, can you speak up? Okay, it's hard to hear with these things in my ears. Um, sorry, here? Agree on the overlap? Yeah, I mean, right, yes, right. It's exactly the condition you need to do the gluing in the sheaf. Right. I mean, and the point is the map from A to sections on the overlap comes from the morphism of schemes on UI intersect UJ, right? And that's the restriction of this global map. Yeah. Sorry, in terms of Attell spaces, like, oh, uh, that's a good question. I mean, right, in that case, the fiber is the actual stalk, and the map is induced by the ring homomorphism on stalks. So I mean, it's telling you something about the structure of those guys. Um, right. I mean, somehow the way I would think about this is that, what this is saying is if you have a function that vanishes at a point, sorry, it's actually more important. If I have a function that vanishes at a point, it pulls back to a function that vanishes at the point, right? That's what this condition says. Um, and since sort of this notion of vanishing as meaning that you're in the corresponding ideal is kind of what makes this whole story run, like you're not really preserving how schemes work if you don't preserve that structure. Okay, cool. All right, so morphisms of schemes are really important because actually, like almost all properties we talk about schemes, we really want to define them as properties of maps, where really sort of that means the property is applying to like the fibers of them. Um, so in particular, it's very, very common to talk about S schemes. So definition, if S is a scheme and S scheme is a pair X a scheme and pi from X to S a morphism of schemes. So these form a category. where a morphism of S schemes is a morphism from the scheme X to the scheme Y that makes this diagram commute. So this kind of, relative categories is very common everywhere in category theory, but it's particularly popular in this world of schemes, where it's sort of, you want to think of everything as a morphism. Now, of course, all right. One thing is, people would never, ever say a spec A scheme, in part just because that's kind of annoying. Technically, that would fit in this mold, but everyone would just say an A scheme or a ring. And that just means a pair like this with X being a map to spec of A. So this is the correct scheme generalization of an A algebra. So an A scheme structure on spec B is the same thing as an A algebra structure on B. So for example, if you are the sort of person who always wants to work in the complex world, well, then you don't really want to think about the category of schemes. You want to think about the category of C schemes. You'll often also hear the word family applied here, where we think about the fibers over the different points of S as being somehow schemes which are related by lying over this guy S. And so it would be called a family. Somehow family really just means a morphism of schemes, but it means a morphism of schemes kind of in the framework where we're thinking about the fibers themselves as the basic objects, but we want to think about how they relate to each other. Any questions? Yeah. Sorry, say that again. Yeah. Um, right. Because, I mean, what's an A scheme structure on spec B? By there, it's a ring homomorphism from A to B, right? So the point is, like, the category of A algebras is the category of rings together with a ring homomorphism from A. And I'm just reversing the arrows and calling them spec. Okay, great. So one, probably the last thing we'll have time to talk about today is, what about maps from spec of A into X? So in general, there isn't sort of a great characterization of these beyond the definition. Um, Such a map is often called an A point. And the reason for this is, well, there are some cases where there's a good characterization of this. So if A is local, then a morphism I from spec of A to X Well, so spec of A has a distinguished point. It has the point corresponding to the maximal ideal. So that has to go to some point in X, which I guess to avoid confusion, I'll call P. So then what sort of structure do I need on the structure sheaves? I need a map I from the local ring at X, at P sharp to A, right? I need a pullback map. And this must be a local homomorphism. Or I should say a morphism of local rings. All right, and it turns out this is all the data you need. A unique way to extend this. Yeah. No, it has a point. There's a distinguished closed point, but there can be other points. So part of what I'm saying here is if I have sort of other primes in here, then there's actually sort of a unique place in X for them to go. Where I think the helpful way to think about this is, well, I can assume that X is affine. I can take some open affine around M. And then I can sort of I get some ring and I start localizing it. All right. So the most important special case of this is, well, a field is a local ring. So if A is a field, a morphism of local rings. So that means a map that kills all of the non-units in the local ring, right? The pre-image of the maximal ideal in the field, 0, has to be the maximal ideal in the local ring. So I have to be taking O of XP, modding out by the maximal ideal, and then mapping in to A, which is necessarily injective. So what this is telling me is if A is a field, an A point is a point in the usual sense, an actual element of the underlying topological space plus an inclusion K of P into. So for example, when we talked about spec of R of X, it was sort of upsetting for people that we had found that the points were not just the real line, but also this other stuff. But if I take the R points, if I take maps from spec of R into here, well, if I take one of the points with complex residue field, I can't, there's no ring homomorphism or from the complex numbers to the real numbers, because it would have to kill I. So the R points really are the prime ideals that come from elements of R. And I should note here, I'm lying a little bit. I'm thinking of this guy as an R scheme in the obvious way, using that R scheme structure, because there are a bunch of really wacky ring homomorphisms from R to R, which are extremely non-continuous, and you probably don't want to think about those. But if you weren't thinking about this guy as an R scheme, then if you thought about this as a Q scheme, then those would be acceptable points. Whereas if I look at spec of C mapping in here, then, well, the guys that have residue field R, well, there's an obvious, unique R homomorphism, R algebra homomorphism from R to C. On the other hand, these guys where the residue field is C, there are two different R algebra homomorphisms from C to C. So if I look at the C points, if I look at the R points, I just get the real line. If I look at the C points, I get the whole complex plane. The point is, this guy isn't canonically C. It's R adjoin a solution of the quadratic equation. So that corresponds to two different C points corresponding to the two different solutions of that quadratic equation in C. So it's once you start thinking about these points that you get like a little closer back to kind of more normal geometry, right? I don't see the generic point because its residue field doesn't map into R or C at all. It has proper, not positive transcendence degree over it. But I do get these kind of more normal things of here's the real line, here's the complex plane. So somehow that more normal geometry is hiding in there, but you have to think about this story of points over different fields. All right, that's all we have time for. So we'll talk about this more next time.